Hi, I am Shiv, and today we are going to be talking about Turing machines. Okay, so I guess most of you are familiar with the movie The Imitation Game. It portrayed Alan Turing, the father of modern computing. Okay, so let's go back to that era. Let's go back to the era of the World War II. During that time, the word computer referred to a human computer. Okay, so what is a human computer? Again, it sounds really strange right now, but at the time, the human computer had four major tasks. The first task was to read an instruction. The second task was to read the symbols on a piece of paper based on the given instructions. Okay, and third task was to change these symbols, replace, change or replace these symbols, change or replace or erase these symbols that were given on a piece of paper. Okay, and the fourth task was to stop when asked to stop. Okay, so Alan Turing devised, okay, why can't we have a machine do all four of these tasks? And thus came into existence the Turing machine. Okay, so this is a formal definition of the Turing machine. So just summing up the theoretical part to the more some of the practical aspects. So in the human computing example, the piece of paper that was given to the human computers, it had some information on it. So we took all of this information and put it on an not infinitely, but like a infinitely long piece of tape, you can say, where we stored all of this information, as you'll see in various other examples that I'll show you in a bit. Okay, so let's go through the definition of a Turing machine. So a Turing machine is a mathematical model which represents an infinite length tape divided into cells based on which input is given. It consists of the head, which reads the input tape. Okay, so now as we discussed, this piece of paper is divided into an infinite length of tape. Okay, and this tape has cells which represents the input. So as I drew a tape over here, this has cells B1, 0, 1. Okay, and the computer, how does the computer know where it is? So we have a head which reads the input tape. Okay, a state register stores the state of the Turing machine. After reading the input symbols, it is replaced with another symbol. Its internal state is changed and it moves from one cell to the left or the right. If the Turing machine reaches the final state, the input string is accepted, otherwise it's rejected. Okay, so that felt a bit overwhelming, but don't worry about it. We'll go through examples and it'll all seem clear. So before we can start, I'll just give you a very basic intuition of how a Turing machine operates. So this is the blank piece of paper that we have. This is the tape, the infinitely long tape we talked about. In this tape, I'm using B to represent data that is not relevant to us, or blank data. Okay, and let's say ones and zeros are the data that we are using. Okay, so let's say this is some input on a tape. Now what we want to do is we want to find if the number of ones and zeros are the same or not. Okay, so over here we talked about something called the head, which reads the input tape. Okay, so over here we'll use a pointer or an arrow to represent the head. So when this program starts, the computer is at the end of the blank tape. It is over here, and the first input it will read is the first cell, which is 1 in this case. Okay, so now how exactly do we do this task? So let me tell you the capabilities of a Turing machine. So a Turing machine can read an input. First part, read an input. Okay, we have read it's 1. Okay, now what can we do? We have options. The first option is we can let 1 be as it is. Second option is we can replace 1 with something else, and we can either go left from here or we can go right from here. Okay, so how do we represent that? So once you read 1, so if the first represents the input, the second option represents what you want to change it with. So if you want to keep it a 1, we'll keep it a 1, and if you want to go right, we'll write right. If you want to go left, we'll go left, and if you want to change it to a 0, so we'll change it to a 0. General nomenclature for a Turing machine, we can say, is the input, or 1 in this case, what we want to replace it with or read, and whether we want to go left or we want to go right. Okay, so this much is clear to you. Now we know what all we can do in a Turing machine. Okay, now let's solve an example. Let's just talk about the intuition of how we are going to solve problems with the Turing machine. So the problem I described to you right now was counting whether we have the same number of 1s and 0s. Okay, so we'll see. We'll start with the machine. We'll see, okay, this is a 1. Fine. We'll move right, okay, and we'll move until we find a 0. Okay, we found a 0. So we'll replace both of these with x's, for instance. And right now I'll just highlight them to green. Okay, so these both are x. We read these both, and these are both x's right now. Okay, and then we'll come back. We'll see, okay, another 1. We'll keep going right until we find a 0. Okay, we found a 0. So we'll replace the 0 with an x. We'll come back and we'll replace the 1 with an x. Okay, then we find another 1. We'll keep going right. Okay, we found another 0. Yep, we'll replace this with an x. We'll replace this with an x. We'll come back. Okay, it's another 1. We'll replace this with an x. Go right until we find a 0. We'll replace this with an x. Okay, so again, anything that you want the Turing machine to do, you'll have to divide it into bit size, like, very small tasks, one cell at a time. So I'll just show you one more, just the intuition of solving the same problem. So let's say we have a 0, a 1, a 0, 0, 1, 1. Okay, and we want to find whether we have the same number of 0s and 1s. So you can obviously see we have 3 1s and we have 3 0s. But how does the machine do it? You start, okay, we have a 0. Okay, if you have a 0, we'll start going right until we find a 1. Okay, we found a 1. So we'll replace the 1 with an x. We'll go back, we'll replace the 0 with an x. Okay, then we'll keep passing through the x's and until we find the next 0 or 1. So we found the 0. Okay, we'll replace it with the next. Keep going right until we find a 1. Found a 1, we'll replace it. Then we'll keep coming back until we find another 0 or 1. We found a 0, we'll replace it with the next. We'll keep going right until we find a 1, and we found a 1. Okay, done. And just suppose in case where this is a false, so suppose there wasn't a 1 over here, then this 0 that you see over here, we are left with the plain 0. It's not a continuous set of x's, so we won't reach the final state. Okay, and thus this string is not acceptable for a Turing machine. Okay, now let's just draw a Turing machine. I just talked a lot about the intuition and stuff. Let's draw a Turing machine to find 1's complement. Okay, so what is 1's complement? So this is a piece of tape, the Turing machine for 1's complement. Okay, so this is a piece of tape where we have blank, 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 1 1 0 0 0, blank, blank, blank. Okay, so in 1's complement you want to replace 1 to a 0 and a 0 to a 1, obviously. So the string this will be changed to this. Okay, let's see how we're gonna do this. Our header is at 1, and what do you wanna do? Okay, so we come to Q0, the first state. Okay, if we find a 1, replace it with 0 and go right. If you find a 0, replace it with a 1 and go right. Okay, so 1 becomes a 0, we go right. 1 becomes a 0, we go right. 0 becomes a 1, we go right. 0 becomes a 1, we go right. 0 becomes a 1, we go right. Okay, and now we are at a blank. Okay, if you are at blank, you're done with the code, you're done with all of this. But again, it is good etiquette or good notation convention for you to return the pointer or the head to where you started. So when you find the blank, go left. and go through Q, okay, Q1, and this time again, if you see, we'll start with a 1. If you see a 1, go keep it as 1, go left. If you see a 0, keep it as 0, go left, until you come at a blank, which is blank. So at the blank, which is Q2, we will be like, okay, on a blank, just go blank, comma, right, and done. We are at the end of this particular code, and we have returned to the pointer to where we started. Okay, let's go through one more example. What do you want to do? Okay, we'll make a Turing machine as a copier this time, as a copier. Okay, so what's a copier again? You take photocopies, you 3D print stuff with 3D printer. So in a copier we have a piece of tape, and say we have 1 1 1 blank blank blank. So in a copier I want you to copy this set of instructions, this string, these set of ones, into the corresponding blanks over here. So the output that we want on our piece of tape will look something like blank 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 1 1 1 1 1 1 blank blank blank. Okay, and again, if this is something else like 1 0 0 1, so blank 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 blank, this will become something like blank 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 1 1 0 0 1 1 0 1 blank blank blank. Okay, yes, okay, let's see how we can make a Turing machine for the same. Okay, so I'll just draw this string over here again, blank 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 1 1 1 blank blank. Okay, now let's see how we are going to make a copier from a Turing machine. So the pointer starts at in 1. The approach we're gonna take now is, okay, I'm gonna bring my pointer one place back from the blank. Okay, now I'm at 1, and I will make this into an X, and then I'll convert this blank into a 1. Then I'll keep going left until I find the next one. I'll convert this into an X, and then keep going right until I find the next blank, which I'll convert into 1, and keep going again. And again, this thing that we're doing from over here can be done from here as well. You can take any number of approaches to solve this. Okay, so let's see how we'll do what I just mentioned. So Q0 1, pointers over here. I want you to keep going 1 comma 1 comma right. Okay, when you see a blank comma blank right now, and go left. Okay, so now my pointer is over here. Now I want you to convert this one into a blank and go right. Yes, so this one into an X, go right. Okay, I am at a blank. Now just in case, let's just go instant by instant, not cover the whole picture right now. So okay, so I made this X 1 into an X, and now I'm at a B. So if it's a B, then convert the B into a 1 and then go left. Okay, so this B is now a 1 and my pointer is at X. Okay, so Q3, if you are at an X, go left. If I'm at an X, comma, go left. And when you see a 1, then let's just loop this up. Yeah. X. Okay, I moved left. The pointer is now at 1, and on a 1 I want you to make it into an X and move right. So again, so we'll just go over here. Okay. And over here I want you to make this into a 1 comma x comma right. Okay, so this is now the pointers over here. So if you see an x, you need to pass through them, so x comma right. Okay, the pointer is now at 1, and okay, so you also need to cross the ones to reach the b's, so we'll have to take care of that as well. Okay, so if you come across a 1 comma right, okay, so we crossed the 1, we are at the b now. So when you see a b comma 1 comma left, okay, so now you moved left, so now the pointer is at a 1, and we did convert this into a 1. Okay, so in this we'll also loop through the ones, 1 comma left, yes, and how do we differentiate with the x's? So let's put it through another state, because right now when we come across a 1, instead of going left, you could also exit the entire loop. So let's add one more state over here, because you'll go through the ones first and then you'll go through the x's. So I will add another state over here, which is q4, and in this state I'll go through the x's, x comma left, and when you do come across the 1, I want you to make it into an x. Okay, so when you come across 1, make it into an x and go right. Okay, so let's see what we go doing. The pointer is at 1. On a 1 we'll go left, then we are at an x now. On an x we'll keep going left, okay, again a left. Now we are at a 1, and when you are at this 1, you'll make this 1 into an x, and you'll go 1 right. Okay, the pointer goes 1 right. You come at an x we'll go right, okay, go right. At an x again we go right. At a 1 we keep going right, until we reach it in b. We'll make this b into 1, and we'll go left. Okay, we'll go through the ones, back, left, x, left. Okay, now we have also returned the pointer back to the original. So we'll just draw one final state over here, which will be something like blank, comma, right, and we'll make this q5. So I've also exited the Turing machine, and again, this thing that we've drawn over here can be done in numerous ways, so don't be worried you have to do exactly like this. Okay, so now you have seen how powerful a Turing machine is as compared to other models that we have studied in Automata till now. Okay, so an astonishing fact about the Turing machines is that obviously you know that all of modern computing is based on the Turing architecture, but even till date there isn't a single problem that modern computing can solve, but that Turing machine can't. So as you see in this photo, there's an open challenge right now, like you can't find a single problem that modern computing can solve that Turing machine can't solve. So if you do have some problems like that, you can grab your $1 million right now. But like again, there is immense research going in fields like quantum computing, which is again a whole new different architecture of computing. So if we do end up getting quantum, like achieving breakthroughs in quantum computing, those could be problems that the Turing machine won't be able to solve. So again, we have seen how powerful a Turing machine now is, and I hope you appreciate the beauty of this. So that was about it from me.
Alright, so if you've reached till here, thank you for watching the whole video. I hope I didn't bore you, and I wish you have a fabulous day ahead. Thank you, bye.